Right now, a neutron star called PSR J0437-4715 is still radiating heat it should have shed billions of years ago, and the physicists at NASA and MIT have no way to explain where that energy is coming from. They have run every model. They have checked every number. And what they found buried in the data is the part they are afraid to say out loud. A neutron star is what remains after a massive star dies. The explosion strips everything away, the outer layers, the atmosphere, the fire. What is left is a compressed ball of matter roughly the size of a city, 12 miles across, but carrying more mass than our entire sun. The gravity is so extreme that a single teaspoon of its material would weigh 1 billion tons on Earth. PSR J0437-4715 sits about 510 light-years away, practically next door in cosmic terms. Astronomers first detected it in 1993 and tagged it as a standard millisecond pulsar, spinning hundreds of times per second, slowly cooling toward silence. That is how every neutron star works. The fire fades, the spin slows, the temperature drops, except this one is not doing that. And the longer scientists watch it, the stranger the numbers get. In 2024, NASA's NICER telescope, mounted on the International Space Station, locked onto PSR J0437-4715 for the most detailed thermal measurement ever attempted on a neutron star. The goal was routine: map the hot spots, confirm the cooling models. Instead, what they measured was a surface temperature that does not match this star's age. Not by a small margin, by billions of years. The star is spinning too fast for something this old. The heat is too high for an object that has been cooling since before our solar system formed. A neutron star of this age should be cold and dim, fading into the background silence of deep space. This one is blazing, still pulsing with energy it has no right to have. The NICER team published the results. The physics community reviewed the data. And then the questions began, because if the cooling model fails here, it fails everywhere. And that opens a door nobody wanted to open. The obvious answer is that something is reheating it: friction from infalling matter, magnetic field decay, particle collisions deep in the core. Researchers checked all of it. The magnetic field is too weak. There is no accretion disk, no material raining down from a companion star. The rotation rate rules out simple friction. One by one, every conventional explanation was laid against the data. One by one, every explanation failed. The physicists at MIT and the Max Planck Institute were left with a temperature reading they could not make disappear. This star is warmer than it has any right to be. Not poetically, precisely. A measured anomaly that no current model of stellar physics can reproduce. Here is the part that should stop you cold. When astrophysicists calculate the age of a star using its cooling rate, its spin-down speed, and its thermal signature, they get a number. For most neutron stars, that number agrees with everything: the age of the galaxy, the timeline of stellar evolution, our cosmological clock. For PSR J0437-4715, the calculation produces an age that does not fit inside the universe we know. Not slightly, deeply. The thermal data suggests this object has been cooling for longer than the universe has had time to cool anything. 13.8 billion years. That is the accepted age of everything. The Big Bang was the clock starting, and yet the residual heat of this star does not sit cleanly inside that window. Some models suggest it is carrying thermal memory from a state that preceded standard cosmology. Others propose exotic matter in the core, strange quarks behaving in ways that trap and slowly release heat across timescales we have no framework to describe. But here is the strange part: it should not be possible at all. Because if a neutron star can carry heat older than the universe itself, we have to ask what that heat is remembering, and why it refuses to go quiet. The implications stretch far beyond one star. Neutron stars are how we test our most extreme physics. They are laboratories we cannot build: densities, pressures, and temperatures that exist nowhere else in nature. When a neutron star behaves as expected, it confirms our models. When it does not, it exposes what those models cannot see. If PSR J0437-4715 contains exotic matter, strange quarks, dark matter concentrations, relics from conditions that existed before standard cosmology applies, then our picture of what matter even is at extreme densities is incomplete. And if our models fail at this density, they may fail at the densities we are extrapolating toward in the early universe. This is not a footnote in a paper nobody reads. This is a crack in the foundation. The star is 510 light-years away, pulsing its impossible heat into space, waiting for us to understand why it is still here. We do not know what is inside PSR J0437-4715. We do not know if the universe is older than we measured, or if matter itself carries a memory we never accounted for. What we know is that this star should not exist the way it does. So tell me in the comments, if our timeline is wrong, what else did we get wrong?